In this video, you'll learn about the basic components of a dynamic system, dynamic equilibrium, gravitational forces, and forces due to support excitation. For the dynamic analysis of structures, it is essential to break down a structure in terms of its mass, stiffness, and capacity to produce damping forces. In summary, the components of a dynamic system are, firstly, the mass, secondly, the damping, and thirdly, the stiffness. Many structures can be idealized as what we call a single degree of freedom system. For example, consider the simple cantilever drawn here. This cantilever has a stiffness equal to K along its entire length, a cross-sectional area, and a mass density. It's subjected to a time-varying load, P of T, applied at its tip, and it has an overall length of L. We observe that under load, the whole structure deflects to a variable degree along its length. We draw the deformed shape. We can see that along the x direction, the deflections are a function of x. As this is also a time varying problem, we can also say that the deflections are a function of time. But the displacement is the degree of freedom that we're interested in. For this example, the deflections are a continuous function of the position x. We also observe that the mass and stiffnesses are distributed along the whole length of the structure. The exact and more complex way of analyzing this type of structure for its dynamic response is to set up what we call a continuum vibration problem. However, we can simplify things by adopting what we call a single degree of freedom representation, where the structural system is approximated by a concentrated mass connected to a linear spring and a damping force generator that we will call a dashpot. This type of system is usually drawn with the mass as a single block on frictionless rollers, connected by a linear spring, which we said has stiffness 3 EI over L cubed, and a dashpot, which generates a certain amount of damping via the damping coefficient called C. The single degree of freedom that we're interested in here is U of T, so we can now see that the displacement only goes in one direction, which is the x direction, and this is allowed to vary with time. The applied loading is taken into account also. Generally, all of these features have to exist in a single degree of freedom system. However, there are some special cases where, for example, the damping force can be zero, and also the applied loading can be zero. We will deal with these later in the course. We can sometimes describe this single degree of freedom as what we call simple translation, which in this case is in the x direction. The objective of a dynamic analysis is to determine the time-varying displacements of our system. An example of such a response is shown here, where we plot time on the x-axis and the displacements as a function of time on the y-axis. To achieve this result, we need to construct an equation of motion which gives the behavior of our system. Typically, this is done by considering the resisting forces of the various components of our dynamic system. If we consider again our mass spring damper system, we can then construct the dynamic equilibrium by considering the forces developed by each of its components. From the mass, we have what's called an inertial force, which we denote by Fit, as indicated here. From the dash pot, we have what's called a damping force, FDT, and from the spring, we have what's called a static force, FST. Mathematically, the equilibrium can be written down as the inertia force plus the damping force plus the static force equal to the externally applied force. Remembering again that the externally applied force can always be set equal to 0. Collectively, the inertia, damping and static forces are what we call resisting forces. And these are in equilibrium with what we call the excitation force. The components of these terms are specified as follows. The inertial force is given by the mass of the structure times by its acceleration. The damping of the structure is given by the damping coefficient times by the velocity of the structure, and the stiffness or static force is given by the stiffness times by the displacement of the structure. We note in terms of notation that u dot t is simply the time derivative of our displacement function. Often structures subjected to dynamic loads move vertically. In such cases, we need to consider the influence of gravitational forces. If we rotate our dynamic system through 90 degrees, so this time it displaces vertically, but this time also including the weight of the structure, then the dynamic equilibrium of this system is then given by the static force, the damping force, the inertia force, the downward action of the structural weight, the externally applied load, and the single displacement degree of freedom. Our equilibrium then becomes the inertial force plus the damping force plus the static force, and that's equated to the externally applied load plus the weight of the structure. What we will now demonstrate is that the equation of motion measured from the initial static displacement of the system caused by the weight of the structure is not affected by gravity forces. The calculated displacements from the equation of motion are for the dynamic response only. To show this, consider the dynamic equilibrium in its statically deformed configuration. The deformed configuration is shown here in red with its corresponding static force, damping force, inertial force, and weight. This then displaces by a certain amount. Due to the weight alone, we have a displacement which we call delta ST, which is the static displacement. Additionally, we have another type of displacement which we'll label U bar T, and this is what we call the dynamic displacement. The total displacement, which is the sum of the static and dynamic displacement, we label as UT, and so we can then say that UT is equal to delta static plus U bar T. Focusing on the static forces, we can write that the static force is equal to the stiffness times by the total displacement, which by substituting in equation 3 we get the stiffness times by the static displacement plus the stiffness times by the dynamic displacement. Substituting this then into the equation of motion will give us the acceleration plus the damping force times by the velocity plus the static displacement times by the stiffness plus the dynamic displacement times by the stiffness, and that's equated to the excitation force plus the weight of the structure. Because the gravity force is not time varying, that has to be considered to be a static force. So equating the two, K times by delta static equal to equal to the weight, we can then say that our inertial force plus our damping force plus our static force is equal to PT, because this term here and this term here by equation 6 cancel out to give equation 7. At the moment, our equation of motion features both ut and u bar t as variables. We need to express this equation as a single variable. Thus, we need to take derivatives of the total displacement ut. So u dot t is equal to the partial with respect to t of the total displacement, and that's then equal to the partial with respect to t of the dynamic displacement plus the partial with respect to t of the static displacement. Because the static displacement is non-time varying, this derivative has to vanish. So we are then left with the time derivative of the total displacement is exactly the same as the time derivative of the dynamic displacement. The same is also true for acceleration. So the effect of gravitational forces can be neglected if the dynamic displacements are measured from the static equilibrium position delta st. That means we can say that our equation of motion, where gravitational forces are present, can be written in terms of u bar t. So in this case we seek to solve for u bar t. In general, we will not make a distinction between ut and u bar t. In subsequent analysis we will just use ut. But for clarity, we can see that if we plot the total response, where we have static displacement plotted as an intercept, the dynamic displacement is plotted here. The total displacement then is simply the dynamic displacement plus the static displacement, which is obviously just a translation of the dynamic displacement. So it is sufficient to measure the displacement from the statically deformed position. One of the major applications of structural dynamics is in the earthquake analysis of structures. Earthquakes do not directly apply forces, they cause ground motion, which is typically lateral in nature. The combination of the structure's mass and the lateral ground motion is what develops a secondary inertial force that we refer to as the effective support excitation. To measure this, consider the following single degree of freedom structure. This structure consists of a rigid mass attached to two columns with stiffnesses of k/2 each. The structure is only allowed to displace laterally, so it is still a single degree of freedom structure. When the structure is subjected to ground motion, it undergoes lateral deformation, shown here in red. And as we said, this is a single degree of freedom motion. The structural dynamic displacement is given by ut. The ground displacement is denoted by ugt, and this is measured with reference to a fixed axis, which I've drawn here. The structure is then built into the ground. The total displacement then, measured from the fixed displacement axis, is given by u superscript t of t, which is equal to the ground displacement plus the structural displacement. The force equilibrium for this system can be obtained by considering first the free body diagram of the structure. So this is the concentrated mass from which it develops static forces, damping forces, and static forces. The damping comes from the dashpot that is drawn on the structure above. Note that the static forces are divided into two because they are shared between the two columns. Equilibrium in this case, because there's no directly applied excitation force, is given by the inertial force plus the damping force plus the static force, this time set equal to 0. For the inertia term, we must consider the effect of ground motion. So, defining this inertia term, this is simply the mass of the structure times by the second derivative of the total displacement. Substituting this back into the equation of motion, which is equation 11, we get mu superscript t of t plus c dot u of t plus kut equal to 0. Looking more closely at the total displacement ut of t, we know that ut of t is equal to ut plus ug of t, where this is the dynamic and this is the ground displacement. If we then take second derivatives of this, we can see that we have u double dot t plus ug double dot t. So, substituting this acceleration term back into our equation of motion for mu superscript t double dot, we get mu double dot t plus mu subscript g double dot t plus cu t plus ku t equal to 0, where this term here has been modified from its original form, which was expressed as the total displacement. We can then rearrange this equation so that on the left-hand side, everything is in terms of a single variable. And on the right-hand side, we have a term minus m u double dot g of t. And this is sometimes known as P effective, which is the effective support excitation.